Dilutions are just the process of adding water or some other solvent, but usually it's water, to reduce the concentration of a solute in a solute. So think about like adding water to OJ. If you buy frozen orange juice, we don't use that anymore in our house, but when I was a kid, that was my job, was diluting the orange juice concentrate when we ran out. And so you'd add, what was it? I think you'd open the little container, dump the frozen orange juice into the pitcher, and add 3 containers full of water. And so you're just diluting the orange juice. It was very concentrated in the frozen solution, and you're diluting it with water. And that's the same thing we do in chemistry. One of the things that makes this easy is this idea, volume, or this principle. Volume and concentration are related by inverse proportion. So if you increase one, you decrease the other. So in the case of orange juice, we had a certain volume. Say that frozen orange juice container contains 250 milliliters of frozen orange juice. So that's our volume, and it's very concentrated. When we dilute that orange juice with water, we're increasing the volume and the concentration is going down. So volume up, concentration down. Volume down, concentration up. If we were dehydrating the orange juice, letting water evaporate out, we would be concentrating the orange juice by reducing the volume. So volume and concentration are related by inverse proportion. You increase one, you decrease the other. So we can write a little law here that we can use. Initial concentration of a solution times the initial volume equals the final concentration times the final volume. Give you a minute to write that down. Initial concentration times initial volume equals the final concentration times the final volume. So it's a pretty handy little equation. And because when volume goes up, concentration goes down, if you multiply the initial concentration times the initial volume, it's going to equal the final concentration times final volume. It doesn't matter which units you use, as long as the units are the same on each side of the equation. So if we had initial concentration in milliliters, the final concentration would have to be in milliliters as well. If the initial volume was in grams per liter, the final volume would be grams per liter as well. So any unit, you can use any units in this equation, but they have to be the same on both sides of the equation. And so there's our equation. C1, initial concentration, times V1, initial volume, equals C2, the final concentration, and times V2, the final volume. So get to know and love this little equation. C1 times V1 equals C2 times V2. Let's do an example. All right, so we have V1 C1 equals V2 C2. So our V1 was 0.9% weight to volume. Our C1 was 25 mils, and that equals C2, or V2, sorry, V2 times C2, which is 75 mil. So if I don't convert to grams per mil, I can simplify this, and I can just divide both sides by 75 mils like I did last time. 75 mils will cancel in the numerator on the right and the denominator on the right. Milliliters will cancel in the numerator and denominator on the left. And what I'm left with is 0.9% weight to volume times 25 divided by 75 equals V2, and V2 just equals 0.3%. So that makes it a lot simpler.
Doctors?
Yes, Anna, go ahead.
0.3%, it's not a volume, though, it's concentration too.
I'm sorry?
0.3% would be the concentration too.
Yes,
not the
exactly.
volume.
It's a weight to volume concentration.
But in the equation you're writing volume too.
I'm sorry, I couldn't hear that last part.
But in the equation you're writing that it is volume too. Because volume
you're,
two
you're right.
70...
Sorry, you're right. I wrote this should be C2. Thank you. All right. Clearly, I've got too many moving parts here. I'm not keeping track very well this morning. So there you go. Should be C2. Let's do another one. How many liters of 6 molar sodium hydroxide solution are needed to prepare 1 liter of a 0.15 molar sodium hydroxide? So this would be a fairly typical example of what you might find in a chemistry lab or in medicine. So what do we know, what do we want here? What's the question? So what we want is how many liters of 6.0 molar sodium hydroxide to use in preparing a 1 liter solution of 0.15 molar. So we're going to take a little bit of the 6 molar fairly concentrated solution and we're going to dilute it. And so what we want is the liters of 6 molar sodium hydroxide to make 1 liter of 0.15 molar sodium hydroxide. What do we know? Well, we know that our starting concentration, C1, is 6 molar. V1 is what we're going to look. That's what we want. We want the number of liters of 6 molar sodium hydroxide. We know C2, that's our target. Concentration 2 is 0.15 molar sodium hydroxide. And V2 is 1 liter. That's what we want to end up. All right, so let's set up our equation. C1, V1, C2, V2. So we have 6 molar sodium hydroxide as our initial concentration. V1 is our unknown. Our concentration 2 is 0.15 molar NaOH, and V2 is 1.0 liters. All right, so how do I isolate V1 on one side of the equal sign? One way to do that is divide each side by 6 molar NaOH. If I do that, now I can do some canceling. So 6 molar in the numerator on the left cancels 6 molar in the denominator. We can cancel some units on the right, molar in the numerator, and molar NaOH in the denominator. And so what do we have? We have V1 equals 0.155 times 1.0 liters divided by 6. And if we do the math there, 0.15 divided by 6 is 0.025 liters. There's our
Looks good to me.
So that's V1. That's V1, volume 1. So we need to use 25 milliliters or 0.025 liters. And then how would we actually prepare that solution? All right, we've answered the question, how many liters of 6 molar sodium hydroxide are needed? And we needed 0.025 liters. So to prepare that solution, we would take 0.025 liters, which is 25 milliliters of NaOH of the 6 molar NaOH. And we would put that in a beaker or a graduated cylinder, and then we'd add water. So the total volume is 1 liter. All right, so that's how we'd actually make the solution. The problem didn't ask us to make the solution. The reason I make that point is that could be a test question. And bringing things to volume by adding water is something we talked about a little bit in class, but you always want to add water at the end to bring the solution up to the required volume. If you start with 1 liter of water and you add a solvent, you'll most likely increase the volume above 1 liter. If you start with 1 liter of water and then you add whatever you want to dissolve, your total volume will be something above 1 liter. So what we do usually is take a little bit of water, add our solute, whatever we're going to dissolve, to that water, and then add enough water to bring the volume up to the total.
So essentially the water dilutes the concentration because you're trying to balance out the whole solution of the of whatever you're trying to make, right? Basically, or
yeah, we're diluting with water up to the target volume.
Okay. And the target volume is always going to be, well, depending on what you're trying to make, because if it's weight over volume or mass over mass, then wait, is this mass over mass or weight over volume?
I think no, in this case we're just talking about a molar concentration. It doesn't have anything to do with mass over mass. So we're talking about molar here. So again, 4 ways of expressing concentration, one of which was molar. And so we want a 0.15 molar solution.
And a molar solution is 1 mole of that said whatever, over the solution of what you're.
Molar is defined as moles per liter.
Okay, the liter solution, which we just found, and that's our answer. Okay.
All right. Any other questions there?
I kind of have like a dumb question just on like the math calculations near the end.
Go for it.
So the reason you don't divide so you're only like dividing the numbers like 0.15 is in molar and is in molar. So is that the reason why you're like dividing them, but you're not dividing like the liter, like the 1.0 liters by 6?
Well, the way it works in multiplying and dividing is you could do it two ways. You could divide the 0.15 by 6. See, well, let's see. I would multiply first and then divide. So let's see if we divided, change it. All right. So no, we basically you would multiply the numerator together. If I was a math teacher, I'd be used to doing this all the time and probably could explain it better. But you'd multiply the numerator together. It looks like we got some people on that aren't. If you could mute yourselves too, if you're not asking a question, that would be great. So multiply the numerator together and then divide by the.
Okay, thank you.
Yeah, I'm sure a math professor would explain. All right. Let's go on to any other questions there. All right. So these are just dilution questions, and again, I will give you on the exam the this equation C1 V1 equals C2 V. All right. So that will be given. You just have to know how. All right. So that's it. All right. Opposite charges attract each other. Hydrogen bonds are one significant intermolecular interaction based on this principle of attract. Pick two molecules and draw them oriented to show how they would hydrogen bond together. All right. Pick two molecules and draw them oriented to show how they would hydrogen bond together. All right. So you can pick any two molecules. Well, let's do ethanol and water again, right? We talked about that in class. CH3, CH2OH is ethanol, and let's hydrogen bond. All right, so let's draw our ethanol so we can orient the molecule. And it's important in hydrogen bonding to show the lone pairs because they do participate as hydrogen bond acceptors. So there's ethanol. I've drawn ethanol. So there are three potential hydrogen bonds. Ethanol. One is to use this hydrogen here on ethanol, the one I'm underlining right now, to use that one as a hydrogen bond accept. So in that case, hydrogen bond donor. Hydrogen is the hydrogen bond donor. In that case, it's going to hydrogen bond with the oxygen on a water, right? So one of the lone pairs of oxygen will be oriented toward that hydrogen on ethanol. And these little parallel lines indicate we have a hydrogen. That's how we indicate a parallel line, right? It's not a covalent bond. It's a hydrogen bond. It's an intermolecular interaction. It's an attraction of one molecule for the other, but it's not a covalent. All right, so that's one of the three hydrogen bonds. We've got two more that we can use. One would be putting a water up here attracted to the lone pair on the oxygen in ethanol. But in this case, the water is going to be oriented so that the hydrogen in the water is facing the lone pair oxygen, and that's our second. Our third hydrogen bond would be on to the other lone pair on ethanol, on the oxygen in ethanol. That I'm drawing right now. That is hydrogen. All right, so that's how you draw hydrogen bond. And just be sure you know hydrogen bonds. It's almost guaranteed there'll be something on hydrogen bonding on the exam. I will likely give you molecules and tell you to draw hydrogen bonding. You won't have to come up with your own like you did. All right, questions there?
Perfect. This was perfectly laid out and easy to follow.
Great. Next one. Oh, I said on the exam, all right, next one. You want to heat up some water for tea. You don't want to boil the water. You just want to heat it from room temperature, 25 degrees. Take that as our room temperature to 90 degrees Celsius. And you need 150 mils to make your cup of tea. How much heat energy in calories do you need to add to the water? All right. So word problem again. What do we want? We want the calories to heat 150 mils of water from 25 degrees C to 90. What do we know? Well, one thing we know is when we're heating up something, if we're not changing the state, if we change the state of something, it would be going from solid to liquid, for example. That would be melting. That would be a change from the solid state to the liquid state. Well, here we're not changing state. We're taking liquid water at 25 degrees and heating it up to 90 degrees. It's still liquid water. So if we're heating but not changing state, we use the specific heat of a subspecific heat. And that'll be given to you on the exam. It'll be given to you for the substance you're heating up. So in the case of liquid water, the specific heat, sorry, again, forgive my bad writing here, specific heat equals 1 calorie per gram for every 1 degree increase. So 1 calorie for every 1 gram and 1 degree increase. increase. All right. So we have here mils of water. We have here in specific heat our grams. So how do we change mils to grams? Well, we have to use the density of water, and that would be given to you too, but you probably remember it is 1 gram per mil. Nice and easy with pure. Oh, sorry, I'm not sure why it keeps jumping. I must be leaning a tablet or something. All right. So what do we want? We want to heat 150 milliliters of water. We want the number of. So let's go 150 mils of water times our specific heat, which is 1 calorie per 1 gram times 1 degree C. And now we need to put in our conversion factor, our density, to convert grams to mils. So we have 1 gram of water per mil. That's our density. So now we can cancel some units. Let's say we can cancel water, mils of water on the far left, crossing that out now, with mils of water in the denominator over on the right. We can cancel grams in the middle there in the denominator with grams in the numerator. And those of you who are alert are probably recognize that I forgot one more factor we need to multiply, which is the number of degrees that we're going to heat this up. So we're going from 25 to 90. So that's an increase of 65 degrees C, 25 to 90, 65 degrees C. And now we can cancel degrees C.
Isn't it 70?
Degrees C. 25 to 90, I think, is 65.
Oh, you're right. I'm silly. I don't know how to do math. My bad.
We've all been math challenged today. So 150 milliliters times 65. My math here says that is 9,750 cal. 9,750. Does the math and gets a different number, let me know. All right, so what we wanted was the calories, and we have an answer in calories, so that's good. Does the math look reasonable? Well, it's going to be 1 calorie for every degree C. We know we're heating it up 65 degrees C, and we're heating 150 grams of water, or 150 mils. So yeah, 9,750 calories looks pretty. Any questions there? All right, go ahead.
Sorry.
Please.
Just thinking about like the formula for this, so you're multiplying the specific heat by how many milliliters you need, by the density of water, by the increase in temperature.
Right. So it's a series of conversions in a way. Yep.
And you'd do those same multiplications for every time you're just trying to see how much heat energy you need.
Exactly. Yeah.
Okay.
Yeah. So I think the book I think the book even says you can use these kind of like conversion factors, but you might look at the book again. I think it has some pretty good explanations, but just to get an intuitive feel, what the specific heat says is how much energy you're going to have to put in to heat something up. And
for this problem, Dr. C, which will be
per gram
provided,
per degrees C. Now, hang on, Brian, let me finish this.
My apologies.
It gives you calories, specific heat gives you calories per gram for every 1 degree increase. So it kind of says, all right, we need to know how many grams we have, and we need to know how many degrees C we're increasing the temperature. Right? Specific heat, its formula itself kind of gives you that. We need grams and we need degrees C, and we had grams. We had to convert grams or we had to convert mils to grams. So that's the use of our conversion factor right here, our convert mils to grams, but that gets us grams. And then our specific heat also asks for the number of degrees Celsius that we have to increase something, and that is in that last term there. And so then we just multiply across. And again, that's where canceling units is really handy, because our ending number is in calories, and that's what we want. That's what we have. Okay. All right. Other questions?
Dr. C, I was wondering what is going to be provided on the exam? What conversion factors are going to be provided? Like, is the specific heat conversion factors going to be provided, or are we got to learn this all on our own?
It'll be provided. If you go to the review guides, it tells you what will be provided for you. So check out the review guide. You add 12 grams of sodium carbonate to some water, and then add enough water to bring the total volume to 500 mil. What's the molar concentration of the carbonate in the solution? And then what's the molar concentration of the sodium? All right. So another word problem. What do we want? Let's do the first part first. We want the molar concentration of carbonate. What do we know? We've got 12 grams grams of sodium carbonate. We know we need to convert grams of sodium carbonate to moles. So for that, we're going to need our converter. So sodium carbonate, let's figure out the formula mass of sodium carbonate. So sodium, we have one sodium. Carbonate is CO3, carbonate C3. So let's add up our atomic mass. We have one carbon, 3 oxygens, and 1 sodium. All right. So let's see. Sodium again is 23. We're going to round 22.99 in the book. 23 sodium. Carbon is going to be 12. And oxygen is 3 times 16, 43 oxygens each of. So if we add those up, we get 60. It looks like 83. All right. So we know that in 1 mole of sodium carbonate. Wait, I've got to add one more thing because sodium carbonate has 2 sodium, right? Remember, CO3 has a -2 charge. So I've actually got 2 sodiums in sodium carbonate. So I need to change my mass, sodium. It's 23 individually, so it'd be 46 total. 2 times my total going to be 46. See, 6106. My apologies here for a lot of the hiccups. I'm doing this a little on the fly here. Thanks for bearing with me. So now,
Wait, where'd you get 106 from? I'm sorry, Professor.
So our 106 is 46 plus 12 plus 48. If I've added that right, so our conversion factor is for every mole of sodium carbonate, we've got 106 grams. All right. So let's convert our 12 grams sodium carbonate to moles of sodium carbonate. So to do that, we take our 12 grams sodium carbonate given in the problem times our conversion factor, which is going to be 1 mole sodium carbonate per 106 grams. And let's see there. That is 0.113. I'm not going to round right now. I'm just going to go 0.113 moles of carbon. So my ending units are right. I wanted moles. I canceled grams. I wanted moles. So that's my ending unit. That looks good. I've got about a little over a tenth of a mole because I started with 12 grams and a mole is 106 grams. That's approximately a tenth. Can kind of do that in my head by 12. If I round 106 to 120, it's an easy 12 divided by 120, and that gives a tenth. So I do that in my head just to give me an idea that the math here looks good.
Dr. C, so when you're canceling out the 12 grams for the sodium squared or base squared or whatever, the Na2CO3, how does that cancel out the grams again?
Well, I didn't write over here, but this is grams sodium.
Oh,
Na2CO3. So to be complete, let's write sodium carbonate here as well. Good point. To be complete, I should have written them both. All right. So now we've got 0.113 moles, and we're looking for a molar concentration, which is moles per liter. All right. So we've got the moles. What's our volume? It's 500 milliliters, right? And we could do be complete. Let's convert 500 mils here on the lower left times 1 liter per 1,000 milliliters. And if we do that, we get 0.5 liters. 500 milliliters, 0 liters. So to get our molar concentration of sodium carbonate, we divide 0.113 moles by 0.5 liters, and that gives us a concentration 0.226 molar. Again, I've done that right. 3 divided by 0.5 is 226 molar. All right. So that is our concentration of sodium carbonate. So
I just have a quick question about that.
Sure, Connor, go ahead.
So if you had asked us what is the molarity, would we have done the same thing versus because our molar concentration and molarity the same thing?
Yes. Molar and molarity. Yeah.
Okay.
Moles is just the count. Molar is moles per liter.
So then technically for a molar concentration, would the answer be 0.226 moles per liter?
Yes.
Or
yeah. Molar, capital M is moles per liter. So we could write 226.
do you care like if we write moles per liter versus just molarity? Like the
No,
capital M?
no, it's the
Okay.
same. Yeah. Capital M is just the abbreviation. So if you wrote moles per liter, if you wrote moles, that's different, but moles per
Yeah.
liter.
Okay.
All right. So if we've got 0.226 molar sodium carbonate, how many moles of carbonate do we? Well, we have one carbonate, right? Carbonate's one of our polyatomic ions that we're memorizing. If we have one carbonate ion for every one sodium carbonate, the moles of carbonate are the same as the moles of the total. It's 1-to-1. So we have 0.226 moles of CO3 in 0.226 or 0.226 molar CO3 in 0.226 sodium carbonate.
I don't understand how you just know all these calculations and numbers and stuff.
So
I keep forgetting you're a doctor, my bad. You're a doctor in chemistry, my bad.
So as I mentioned, so there's one carbonate in every sodium carbonate.
It's like 100 an hour, right? Yeah.
Yeah. So sodium carbonate would be 2 sodium ions and 1 carbonate. So the relationship between sodium carbonate and just carbonate is 1-to-1 relationship. 1 carbonate in every formula unit of sodium carbonate. In every formula unit of sodium carbonate, we actually have 2 sodium. So we have actually 2 moles of sodium, or 0.452 molar sodium in 0.226 molar sodium carbon, running out of space. All right. So every formula unit of sodium carbonate has 2 sodium. So if we have a molar concentration in our beaker, 0.226 molar sodium carbonate, we actually have 2 moles of sodium for every mole of sodium carbonate. So our molar concentration of sodium is 0.4. And that combines a lot. The reason I went through this question was this will be one of the harder ones that would be on the exam, because we've got a lot of principle, right? We converted moles to grams, or grams to moles in this case, and we understood the relationship between sodium, with the number of sodiums per carbonate, number of sodium ions per carbonate ion, and then we had to figure out the number of moles given the overall formula of sodium carbonate, just 2 sodiums. And
so is the answer for this problem 0.226 molar?
So I asked for a couple things in the problem: the molar concentration of carbonate, which is 0.226, and the molar concentration of sodium. That was the last line there, and that is 0.452 mole sodium. So with two answers. I probably won't be asking you for both on the exam, but in this example, it was 2. I'm making a stock solution, or a solution of hydrochloric acid, and I have a stock solution in my lab that is, hang on here, readjust my screen a bit here. All right, our stock solution is 6 molar concentration of hydrochloric. How many milliliters of this stock solution would I need to make 1 liter of a 0.75 molar solution of hydrochloric acid? All right, so another word problem. What do we want in this problem? So what the problem is asking for, what it wants, is the milliliters of 6 molar HCl to make 1 liter of 0.75 mole CL. So we're just diluting. We're diluting just like you dilute orange, another dilution. So in our dilution problems, well, what do we know here? We know that to figure out a dilution, we use C1V1 equals C2V2. We know our starting concentration is 6 molar. That's our stock solution, 6 molar HCl, and our volume is our question. We want to know how much 6 molar HCl used. Our ending concentration is C2, and we know that is 0.75 molar, and V2 is 1 liter. So that's what we know, and that should be everything we need to solve. So let's set up our equation with C1, 6 molar HCl, times V1, that's our unknown, equals 0.75 molar times 1 liter. So that's our equation, and now we're going to solve for V1. So if I want to isolate V1 on one side of the equal sign, well, one way to do that would be to divide both sides by 6 molar HCl. Now I can cancel 6 molar HCl on the left in the numerator and the denominator, and I've got V1. Oh, and I can also cancel molar, and actually I should say this 0.75 should have been molar HCl. So I cancel molar HCl on the right side in the numerator and in the denominator. So I can simplify this formula then as 0.75 times 1 liter divided by 6. And if we do the math there, 0.75 times 1 divided by
class, stop.
6, I get 0.125 liters of HCl, right? That's the volume of the stock solution that I need. All right. It was asking for liters. My ending units are liters, so that looks good. It's a fairly small volume, but that makes sense because I'm diluting from a 6 molar concentration at the start down to a 0.75 mole. So it makes sense that it'd be a fairly small amount. All right, and Anna, you've got a question?
Yes. The question is how many milliliters? So we need to translate that in milliliters, right?
Let's see. Oh, very good. I asked for milliliters. So let's do another conversion, and that would be using our conversion factor for liters to milliliters. So it's 1,000 milliliters per liter. And so that equals 125 milliliters. All right. And that's how much of our stock solution we need. That was the answer. Need any other questions?
So for using the formula of C1V1 equals C2V2, do you use it when you need to find like a solution? Like is the keyword like solution or concentration?
Yeah, the key word is dilution, really. And that means you're taking one solution and diluting it down to a lower.
One problem that I do have is trying to distinguish whether or not how to, like, if I'm going to calculate the mass over mass or this and that, because I know how to like set up the formulas and what numbers to plug in, but sometimes the problems are worded a certain way and I don't know. Sorry, I guess I would just have to read it.
So I think it'd be good to let's take that offline, Brian. We can work some specific examples. The reason I set up the word problems this way is there's a little formula to doing word problems, and one is to figure out what you want and then figure out what is given and what you know in the problem. And if you go through that, oftentimes it'll make clear what it is you have, what you know, and what you want to do to solve the word problem. So you can try that formula. But for now, we are out of time. We came right up to 10:30. Thanks so much for hanging in, everybody. My apologies for having to do this a little on the fly, and it was a little choppy, but I appreciate you hanging in. I hope the problems were helpful. Please let me know questions related to any of this. Just shoot me an email. And the review guides are all out there on Canvas. And I will get back to you with some instructions for the exam on Monday, and see you all then. Thanks again.
Thank you. Thank you so much, Dr. C.
Thank you.
Thank you.
And I will see you tomorrow, Dr. C.
That's right.
All righty. Have a good one.
All right. You too.